Hello students, welcome to module number 4. In this module, we'll discuss about the digital electronics. Now, in this first lecture of this module, we'll introduce what digital electronics is and what is Boolean algebra that is used in digital electronics or digital computers. Also, we'll introduce some logical operations which are required in Boolean algebra. Now, before going to digital electronics in detail, let us have a brief idea about analog signal and digital signal. Now, analog signal is a continuous signal value which at any instant lies within the range of a maximum and minimum value. That means the analog signal is a signal which vary continuously, but that will lie within a maximum and minimum value. On the other hand, a digital signal is a discontinuous signal which appears in steps of predetermined levels rather than having continuous change. In order to have a clear picturization of analog and digital signal, we can draw them like this. Now, in this plot, the signal which is represented by the red line is varying between plus 5 volt and minus 5 volt, but that variation is continuous with respect to time t. And if you want to represent mathematically, this variation of the signal can be represented as V equal to V naught sin omega t, where V naught is the maximum or minimum value. Similarly, if we want to represent the digital signal, this is the representation of a digital signal where the signal is having only two predetermined levels. One is plus 5 volt and one is 0 volt. And in digital electronics, we represent this plus 5 volt as 1 and this 0 volt as logical 0. Or sometimes we represent this plus 5 volt as on state and 0 volt as off state. A digital circuit is an electrical or electronic circuit which operates only in these two states, or which operate in this binary mode having on and off states or 1 and 0 state. In digital system, high value of voltage such as plus 10 volt or plus 5 volt is represented by a on state or 1 state, whereas low value of voltage such as 0 volt or minus 5 volt or minus 10 volt sometime is represented by a off state or 0 state. So this is the difference between a analog signal and digital signal, and a electronic circuit or electrical circuit which operates with these two states 1 and 0 state is said to be a digital circuit. And the branch of electronics which deal with only such circuits, such digital circuits which operates in this on state and off state is said to be digital electronics. Let me repeat again. The branch of electronics which deals with such digital circuit which operates in the 1 state and 0 state is called as digital electronics. Now, before jumping into digital electronics, we should have little knowledge about the number system. In digital electronics, all digital circuits use binary number system, and binary number system is a system which uses only two digits, that is 0 and 1. Examples of binary systems, examples of digital electronics which uses binary system is your computer. Your computer understands only 0 and 1. It doesn't understand anything else than 0 and 1. So this computer, which is a digital circuit and which comes in the regime of digital electronics, uses only two states, 0 and 1 state, and that system which uses these two states is called binary number system. But the problem arises when you have to give some information to computer, or when you want that computer to understand some other numbers, for example 6, 7, 9 or 10. If you want your system, computer system, to understand 6, 7 or 9 and 10, then how to give those inputs to that system? And a system in which the total number of states or total number of numbers are 10 is called a decimal number system. So the decimal number system, which has base or radix 10, has 10 digits in the system, and those 10 digits are starting from 0, 1, 2, 3 up to 9. And the system in the number system which uses these 10 digits is called a decimal number system. Now if we want our computer to understand a number from the decimal number system, then we must have to convert this decimal number into a binary number, and after that we can give that information to that computer so that it can understand. So we must convert one decimal number into a binary number before feeding it to the digital electronics or digital circuit such as computer. And there is a way to convert that. We are not going to discuss that way, but for the sake of understanding, this is the table representing the relation between a decimal number and a binary number. For example, if the decimal number is 0, then in binary form it can be represented as 0000 as shown in this table, first one. If the decimal number is 1, then in binary system that can be represented as 0001. If the decimal number is 2, binary number is 0010. Like that, if the decimal number is 9, binary number is 1001. So you can see that all these decimal numbers can be represented by binary numbers. Binary numbers means in these numbers only there are two digits, 1 and 0. Okay, and using these you can represent any decimal numbers, suppose 10, 11, 12, 13, 14, 15, 20, 50, 90, any decimal number you can represent using these binary numbers, and there is a way to convert from decimal to binary. Okay, and those ways you will be learning in your higher class or in mathematics. So every decimal number can be represented by a binary number system, and we need to give these binary numbers as information to our digital circuit or digital electronics. Now after giving those binary numbers to the computer, that computer need to process those information for certain operation. That process can be done using some algebra that is called Boolean algebra. So Boolean algebra is required to solve logical problems in digital circuits. Boolean algebra is an algebra which is required to solve logical problems in digital circuits. It is described as the algebra of logic or algebra of two values. So this Boolean algebra is used only in binary number system, only by digital circuits. The term logic means a statement having binary decision or two value decisions. This term logic, algebra of logic, means it is a statement having binary decision or two value decision, either yes or no, either on or off, either 1 or 0. Only two values decisions are there for any statement. Now the two values or states represent either true or false, on or off, high or low, closed or open, 1 or 0, anything. Okay. Now Boolean algebra is used to perform the logical operation in digital computers. After feeding those binary numbers, which are the conversion of decimal numbers, as a information to the computer, that computer need to process those information for certain applications, or as instructed by us, as it instructed by the human being. And basically there are three logical operations which a digital computer perform in the binary number system or in the binary numbers to get the processed output. Those logical operations are: one is AND operation, which is also called as conjunction; one is OR operation, which is also called as disjunction; and one is NOT operation, which is called as negation or complement. These are the three basic Boolean operation or logical operations that are being performed by digital computers in order to follow our command, or in order to process those given information as per our instructions. Okay, now we will discuss in detail about these logical operation: AND operation, OR operation, and NOT operation. Now OR operation. What is OR operation? OR operation is represented by a symbol plus. Its Boolean expression is something like this: if Y is the output and A and B are two inputs, then A plus B is said to be the OR operation. If A and B are two inputs, then A plus B is said to be a Boolean OR operation. See, this output Y is the output of OR operation between the inputs A and B. It is read by Y equals A or B. Y equals A, not plus A or B. The sign is plus, but you should not read it as A plus B. Y equals A or B. Logically it is A or B. It means that if A is true or B is true, then Y will be true. Or if A is high or B is high, then Y will be high. The meaning of this statement, this logical statement, Y equal to A or B, is that if A is true or B is true, then Y will be true. We'll see an example for this. Let us consider this circuit. This is an electrical circuit. This is a bulb. That bulb is connected to a battery through two switches. This is one switch, this is one switch. Suppose this switch is A and this switch is B. Okay. Now one terminal of the battery is connected to one terminal of the bulb directly, and the other terminal of the battery is connected to the other terminal of the bulb through these two switches A and B. Now if both the switches are off, means the switches are not connected, A is also not connected, B is also not connected. If both the switches are off, that means in zero state, then the bulb is not glowing, right? This bulb is not glowing. That means the output is also 0. If both the switches A and B are in off state or 0, then the output will also be 0. Now if one of the switch is on and one of the switch is off, now suppose B is on and A is off, then the bulb will glow. That means Y is on. That means Y is 1. If A is 0, B is 1, then Y is 1. Here 1 represents the glowing of bulb and 0 represents is the not glowing of bulb. Now in the third case, if A is on, B is off, then also the bulb will glow, right? And in fourth case, if both are on, A is also on, B is also on, this switch will glow. So let me repeat all these processes again. Now these are two switches. First case, switch B is on, A is off, then Y is on. Second case, switch A is on, B is off, then also Y is on. Third case, both A and B are off, then this Y is off, bulb is not glowing. Fourth case, if both are on, then also this bulb is on, that means it is glowing. And this is simply justifying this statement. If either of A or B or both are true, then this Y output will be true. Or if A is 1 or B is 1 or both are 1, then Y will be equal to 1. Now if I want to represent this through a table, that's called a truth table, then we can write that if switch A is off and B is off, bulb was off. Switch A is off, B was on, then bulb was on. This is on, off, bulb was on, bulb was on. What this table is showing? This table is showing that if either A is on or B is on or both are on, then the bulb is on, and the bulb is off only in the case when both are off. This table is representing this statement, isn't it? So a table of values which justify or which explain a logical statement is called a truth table. So this circuit is representing the OR operation, which is nothing but, what is OR operation? If A is true or B is true, then Y will be true. Now let us discuss AND operation. AND operation is a operation which is represented by a dot sign. Like multiplication, it is represented by a dot sign. Its Boolean expression is Y equals to A dot B. This is the Boolean expression, okay, and it read as Y equals A and B. The Boolean expression of AND operation is Y equals to A and B. This means Y is the output which we are getting as a result of AND operation between inputs A and B. Y is a output which we are getting as a result of AND operation between A and B, and it reads as Y equals A and B. You should not read it as Y equals to A into B. It reads as Y equals A and B. It means that this logical operation, this AND operation means that if both A and B are true, then only Y will be true. Let us have a electrical analog circuit or in an electrical analogy of this logical statement. Let us consider this electrical circuit where again the bulb, there is a bulb and the bulb is connected to a battery. One terminal of the bulb is connected to a battery, the other terminal of the bulb is connected to the other terminal of the battery through two switches A and B. Now suppose switch B is closed. If the switch B is closed, do you think this bulb will glow? No, this bulb will not glow. Now second case, if switch A is closed and B is open, then also this bulb will not glow because this is an open circuit. There is no connection between these two terminals, right? In first case, switch A was open and switch B is closed, then also the bulb is not glowing. In second case, switch B is open, switch A is closed, then also this bulb is not glowing. Now if both are closed, if switch A and B both are closed, then only this bulb is glowing. Okay. So if I want to represent this case, this electrical circuit through a truth table, through a table of values, then if switch A is off, switch B is off, then bulb is off. If switch A is off, B is on, then also bulb is off. If switch A is on, B is off, then also bulb is off. And the bulb is going to glow only when both switches A and B are on. If both switches A and B are on, then this bulb is going to glow. So obviously this table of values is representing the operation of this circuit, and this table is representing the logical operation defined by this logical statement. What is that logical statement? If both A and B are true, if both A and B are true, then only Y will be true. This is the logical statement, and this logical statement is being satisfied by this truth table, and hence this electrical circuit is representing this logical statement, and this operation is called AND operation. Now let us discuss the NOT operation. NOT operation is represented by a apostrophe s or by a bar on the top of that variable, and its Boolean expression is y equal to a apostrophe s or a bar. Okay, it can be represented by any one of these, and the meaning of this is that if y is the output, which is represented by a bar, then y is the output of NOT operation on A. Now it is read as y equals not A, means y equals A NOT or not A. And the logical meaning of this NOT operation is that if A is true, then y will be false, or if A is false, then y will be true. That means the output will be the other binary value. If A is having a binary value either 1 or 0, then the output will be the other binary value. That means if A is 1, then y output will be 0 after NOT operation. If A is 0, then output y will be 1 after NOT operation. And the electrical analog circuit for realizing this logical operation is this one. Here again the bulb is connected to the battery. One terminal of the bulb is connected to one terminal of the battery, and the other terminal of the bulb is connected to the other terminal of the battery through a shifting switch. The switch can shift from here to here. Okay. In this circuit, in the first case, this A switch is off. This switch is in off state, right? This is in off state. Then the bulb is glowing. That means Y is in on state. In the second case, now the switch is in on state. This switch is straight. That means it is on state. This is, if the switch is straight, this is on state. If the switch is inclined with an angle, then that is called off state. So in the first case, if the switch is in off state, then Y is in on state. That means Y is 1. Then if the switch is in on state, then the output Y is off. Okay. So the truth table for this is, if switch A is in off state, then bulb is glowing, that is on. If the switch is in on state, then the bulb is not glowing, that is off. And this table is representing this NOT operation clearly. So these are the three basic logical operations which a digital computer perform using Boolean algebra, or these are the three basic logical operations which Boolean algebra use to perform tasks using digital computers. But we need to realize these in terms of electronic circuit, not using electrical circuit. Now if we realize these operations using some digital circuit which can be analyzed with the help of Boolean algebra, then those digital circuits are called logic circuit or logic gate. Let me repeat again. If these logical operations are realized by some electronic circuit which can be analyzed with the help of Boolean algebra, then those circuits are called logic circuits or logic gate. So a logic gate can have 2 or more inputs. A logic gate can have 2 inputs, 3 inputs or 4 inputs, but only one output, where the values of output will be either 1 or 0. There are 3 fundamental logic gates similar to the 3 fundamental logic operations which are being used in Boolean algebra. And these fundamental logic gates are OR gate, AND gate and NOT gate. Similar to the 3 fundamental logical operations which are being used in Boolean algebra, there are basically 3 fundamental logic gates, namely OR gate, AND gate and NOT gate. These gates are electronic circuits. Now what is a truth table? The operation of a logic gate or circuit can be represented by a table which contains all possible inputs and their corresponding outputs is called a truth table. If there are n inputs in any logic gate, then there will be n square possible input combinations. For example, if there are 2 inputs to a logic gate, then there will be 2 to the power 2, that means 4 combinations are possible. For example, if there are 2 inputs, then inputs number A and inputs number B, then we can have combination 0, 1, 1, 0, 0, 0, 1, 1, 4 combinations are possible. Similarly, if there are 3 inputs, then there will be 9 combinations possible. 3 to the power 2, that is equal to 9 combinations possible. 3 square is 9. Similarly, if there are 4 inputs, then 16 combinations of inputs will be possible. Okay. The 0 and 1 inputs are taken in the order of ascending decimal numbers for easy understanding of analysis. Ascending decimal numbers means 0, 1, 2, 3, 4, 5, 6, 7 like that, and all inputs, all combination of inputs are written on the truth table in this order. Universally, this, I mean, it's not wrong to write in any order, but universally we follow a certain rule. That rule is that these combinations of inputs, 0 and 1 inputs, are written in the truth table in the ascending order of decimal numbers. For example, this is an example of 4 input logic gate. So if it is a 4 input logic gate, there are 4 inputs A, B, C and D, and obviously there will be 16 number of input combination possible. So we start with 0. This is 0. This decimal value of this combination 0, 0, 0, 0 is 0. Then decimal value combination of decimal value of this combination 0, 0, 0, 1 is 1. Then 2, then 3, then 4, like that up to 15. This is the decimal equivalence of 15. So if it is a 4 input gate, we write the truth table in this order for easy understanding and easy analysis. Okay. So these were all about basics of digital electronics and digital logic operations, some basic logic operations, logic gates, and how to write truth tables. These things we discussed in today's class. In the next class, we will discuss how to realize these logic gates, basic logic gates, through electronic circuit. In the next class, we will discuss these logic gates through electronic circuits. Thank you.